In a previous video, I repaired this old scanning electron microscope. Today, we're going to convert my scanning electron microscope into a transmission electron microscope by making this. Okay, first things first. What is a transmission electron microscope, and why do I want one? Well, the simple answer is that a transmission electron microscope can see things that a scanning electron microscope cannot. However, to fully understand that statement, we need to talk about how an electron microscope actually works. You see, all electron microscopes use electrons to create an image, but the exact way that those electrons are used to create the image differs depending on what type of microscope you're using. In a scanning electron microscope, or SEM for short, images are usually created using something called secondary electrons. There are other methods, but secondary electron imaging is definitely the most common. Here's how it works. We shoot high-energy electrons at a single spot on our subject to be imaged. This high-energy electron crashes into a sample surface and interacts with one of its atoms, transferring a small fraction of its energy to an electron in the atom. This energy, while small compared to the incoming electron, is still more than enough to eject the electron from the atom. We call these low-energy ejected electrons secondary electrons. And to avoid confusion, we call the high-energy incident electrons primary electrons. Even though we've already caused the emission of a secondary electron, that's not the end of the journey for the primary electron. You see, even though it's lost a little energy, it still has more than enough to continue onward, smashing into more atoms and liberating more and more secondary electrons before it is either absorbed or escapes the sample. This is fortunate because it means that for every one input primary electron, we can get many output secondary electrons. Inside our microscope, we have an electron detector. This detector has a small positive voltage on it, which attracts electrons. However, the high-energy primary electrons move so fast that they are essentially unaffected. The low-energy secondary electrons, however, move slowly enough that they can be sucked into the detector where they are counted and turned into a brightness value for a single pixel in our image. By scanning across the subject, we can build up our complete image, pixel by pixel. Secondary electron images like this are probably the most common type of image in scanning electron microscopy. However, there is a major downside. Because secondary electrons are generated at the surface of the sample, the resulting image only contains details about the sample's surface, and tells you nothing about internal features. This makes scanning electron microscopes well suited to imaging things like integrated circuits, but poorly suited to imaging the internal structure of cells and tissues without special preparation. Here is a secondary electron image of a white blood cell. We can see the outer surface clearly, but we don't get a direct view of the organelles inside. In order to see internal structures like nuclei, mitochondria, and internal membranes, we need to look at more than just the cell's surface. A secondary electron image isn't going to cut it here. So what do we do? Well, this is where the transmission electron microscope comes in. In a transmission electron microscope, or TEM for short, the imaging is done using transmitted electrons instead of secondary electrons. Here's how it works. We shoot high-energy electrons through a thin sample. This sample must be thin enough that a significant portion of the electrons will pass through. The electrons that pass straight through are called transmitted electrons. Some electrons pass through, but get deflected by the atoms in the material. These are called scattered electrons, while some electrons get absorbed altogether. To capture a transmission image, we install a detector directly below the sample and measure the number of transmitted electrons. This becomes our final image. Here is a transmission electron image of a white blood cell. If we compare it to the secondary electron image from earlier, you can see that the TEM image contains far more details about the internal workings of the cell. This makes transmission images vastly more useful for diagnosing problems with cellular machinery. However, a TEM isn't always better than an SEM. The SEM and TEM are two different tools, each with different purposes. But given that I have a working SEM, I can't help but wonder, can I convert it to a working TEM? Well, the answer is no, but also yes. You see, we can't turn the SEM into a true TEM, but we can trick the SEM into giving us a transmission electron image. Here's how. Let's say we put a thin specimen in our SEM. When a primary electron from the beam reaches our subject, one of two main things is going to happen. Some primary electrons will interact with the sample and generate secondary electrons from the sample itself. Let's call those group A. Other electrons may transmit through the sample. These are the electrons that would make up a transmission image in a normal TEM, but our SEM doesn't have a detector capable of seeing them. But if those electrons strike another surface, then they will generate an entirely different set of secondary electrons of their own. Let's call those electrons group B. Group A secondary electrons constitute our normal SEM image. Group B secondary electrons, however, constitute our transmission image. But now we have a problem. The detector in the SEM detects all secondary electrons, so both group A and group B electrons will be measured. So the resulting image is going to be some weird hybrid of a secondary electron and a transmission electron image. If we want to view our transmission electron image only, then we need to block all group A secondary electrons from reaching the detector. We can do that by installing some kind of conductive shield around the sample. If the shield is made correctly, it will block the group A electrons without affecting the primary electrons or the group B secondary electrons. That way, only group B secondary electrons will reach the detector, and thus our displayed image will be a pure transmission electron image. This is how we can convert our SEM into an STEM, or Scanning Transmission Electron Microscope. The only thing we need is a relatively simple adapter. These adapters are actually fairly common, though like most lab equipment, they are ludicrously overpriced. So I decided to make my own. Okay, so the first step in making this work is to figure out exactly how much space we have to work with. So let's fire up the microscope and vent the chamber to atmosphere. Let's take a look. Okay, there are three main things to note here. First, we have the sample stage. This is where we normally mount the things that we want to image. This stage is fairly simple and has the ability to move forward and back, left and right, and also rotate and tilt. This stage also has this little dovetail joint that allows us to slide different sample holders on and off quickly and easily. The next thing to note is the objective lens here. Most of the lens is not visible from here, but you can see this copper-colored bit. That's the objective lens aperture holder, and it's the lowest part of the lens assembly. Anything we add to the chamber must clear that piece, or we will damage the SEM. Lastly, we have the secondary electron detector here in the corner. Fortunately for us, this component is so far away that we don't really have to worry about bonking it. Really, the only critical measurement here is the distance from the top of the sample holder to the bottom of the objective lens. The only problem is that we can only measure that distance with the door closed. I carefully stacked some gauge blocks on the sample holder and peered through the tiny gap as I closed the door. It looks like we have just over 0.55 inches. That is not a lot of space to work with. However, I have an idea. See this sample holder? This thing has way more meat on it than necessary. If I were to copy this design but make it more low profile, I could claw back at least a quarter inch or so. That might just be enough. I made a quick mock-up of my version of the STEM-in-SEM Adapter. You can see that I've made a low-profile dovetail adapter here, and on top of that I have this piece that holds the sample grid here. In addition, I have this movable mirror, for lack of a better term, which will generate the secondary electrons. This piece is able to be rotated so we can find and set the optimal angle. Lastly, I have a spot on top that will allow us to mount a shield to block the unwanted group A secondary electrons. Well, I guess it's time to make this thing. I'm going to start by making the base first. Whenever I'm prototyping, I like to start with aluminum because it's easy to machine. Let's get this set up on my lathe. Darn. Small lathe problems. The spindle bore is only 1 inch. No worries, we can just shorten the aluminum piece on the bandsaw first. Now we're in business. I start by facing the end of the rod, then I clean up the outer diameter. This allows me to measure the current size and then enter the value in the DRO. Now I can bring the outer diameter down to the correct size. Looking good so far? Next, I use my parting tool to cut off a disc of the material. The parting tool left behind a little nub, so we're going to have to remove that. This gives me an excuse to use one of my favorite lathe tools. This thing is called a lathe spider. It slides onto my 4-jaw chuck, allowing us to grip thin parts like this and ensuring that the faces are perfectly square to the chuck. Now we can cut the second face and bring the disc to its proper thickness. Now I transfer the disc to the milling machine. As a reminder, I'm trying to replicate this dovetail slot here so that the disc can be mounted in the SEM. The first step of that is to cut a flat face to a specific depth on one side. This flat will also allow us to mount the disc horizontally in the vise. The slot for the dovetail is 1/10 of an inch deep, and I was worried that I might not clear the vise jaws. However, it looks like we just made it. I start by using an end mill to cut the slot to the correct depth. Then I side mill to bring the slot to the proper width. I swap my end mill into dovetail mode and start to cut the angled faces into the slot. Measuring the width of dovetail slots can be a little difficult, so I just pulled the mating piece out of the SEM and used it to ensure a good fit. Perfect. Now I need to drill the mounting holes in the top. The alignment of these holes isn't critical, so I just blued the surface and used a pair of cheap calipers to find the center. This will be good enough. I then put the piece back on the mill, using a center drill first to ensure that the drill bit stays on target. Finally, I tap both holes with an M3 thread. Now I just need to clean off the ink with acetone, and we are done with the base. Now it's time to make the sample holder assembly. I've got the remainder of the aluminum rod from earlier, and I'm going to start by drilling out the central bore, which is the path the electron beam will take. I'm doing this first because I will be using it to reference the center of the part for all the other machining operations. Next, I'm going to use the lathe to form any of the remaining circular features before moving on to the milling machine. While I'm here, I'm going to use the lathe to remove as much of the unwanted material as possible. I find that when it comes to small machine tools, lathes are generally faster than milling machines at removing material, so this will also save me some time. After that's done, I use a slightly larger drill than before and drill just a few millimeters in. This will form the step where the TEM grid will rest. Now all that's left is to use the parting tool to remove the sample holder from what remains, flip it around, and face the backside to bring the flange to its proper thickness. Alright, that's everything on the lathe. Time to move the part to the mill. Again, the first thing I do is machine a flat spot so that later, when this part goes back in the vise, I can guarantee it's facing in the proper direction. Then I mill a slot into the sample holder. This is where the movable mirror will be mounted. After that, I trim the excess from the edges. Looking good so far. Next, I reposition the sample holder vertically and drill the matching mounting holes so that it will screw into the base we made earlier. I almost forgot. We need one more hole here for the shaft around which the mirror pivots. Perfect. The last feature to make is this tiny slot in the top collar. This is needed because it allows us to get a pair of fine-tipped tweezers in and grab the tiny 3mm TEM grid. Unfortunately, my mill is not capable of the speeds necessary to run such a tiny end mill. So to make this slot, I just used a Dremel cutoff wheel. This should be good enough. Okay, time to make the movable mirror. This part is pretty simple, but the order of operations really matters for small parts like this. We start with an aluminum rod and then clean up the diameter. Then we machine the tiny 3mm shaft first. After that, we machine the mirror's outside diameter. Once that's finished, I can test to see if the shaft will fit in the sample holder. It's close, but a little snug. A little bit of sanding with some 1000 grit sandpaper should do the trick. That's more like it. Now I'm going to part off the mirror. However, I'm including a large chunk of extra material because we need to have something substantial that we can hold in the vise. If we don't leave this part, we'd be forced to hold it by the tiny shaft, which is far too small to withstand such abuse. Now I can use an end mill to machine the flat side of this part. Perfect. Now I take it back to the lathe and use a parting tool to separate the finished mirror from the extra material. I'll go hit the edges with a file off camera. The last part I need is the shield. This piece is really simple. Just a small piece of aluminum tubing that fits neatly over the top collar. Awesome. Before we put anything in the SEM, we need to clean the parts to remove any oils or metal dust. I wash them with soap and water first, then give them a quick bath in acetone. Finally, it's time to test the STEM-in-SEM adapter for real. I first reinstall the mounting bracket that I removed earlier. Then I slide on the aluminum base plate and screw the sample holder onto that. Next comes the movable mirror. For the first test, I want to see what it looks like empty, without a TEM grid or shield installed. Okay, fingers crossed. Let's see what we have so far. Where are we? Oh, I found one of the screws. That should mean our destination is nearby. There we are. This is the spot where the TEM grid will be inserted. You can see the 2mm slots that allow for insertion of the fine tweezer tips. You can also see the mirror below. Something that is important to note here is that the inside walls are glowing brightly. This is because the electron beam is striking the walls and causing them to emit a lot of secondary electrons. Installing the shield should fix that. Okay, time to add the TEM grid and shield. I vent the chamber to atmosphere and add a blank grid to the sample holder. Then I install the shield on top, and rotate the entire assembly so the mirror is pointed roughly at the detector. Alright, let's go. Nice, I can see the metal grid. Let me fiddle with the video settings and see if I can improve the picture. That's a little better. However, the contrast still seems low. As a reminder, contrast is the difference between the brightest and darkest pixels in an image. Even if your image is very sharp, it's difficult to make out details if the contrast is low. If we want maximum detail, we need maximum contrast. In a TEM, contrast comes from the difference between the darkest areas, those that block all electrons, such as the metal grid, and the brightest areas, in this case the electron mirror below the grid. To achieve maximum contrast, we need to do whatever we can to both make the grid as dark as possible and make the electron mirror below as bright as possible. This will give us the best possible image quality in our transmission electron image. As you can see here, our contrast is a little low. The mirror below could definitely be brighter, and the grid isn't totally black either. I have a couple ideas on how to improve the contrast. The first is to take advantage of the movable mirror. Remember earlier how the vertical edges of the aluminum pieces were bright compared to the flat faces? Well, that's because the angle of a piece of material relative to the electron beam greatly affects the amount of secondary electrons emitted. This is why I made the mirror movable, to determine the angle at which the detector captures the most secondary electrons. The only problem is, I can't exactly stick my hand into the microscope and pivot the mirror while the electron beam is on and the system is under a high vacuum. I think I have an idea. If we look at the sample stage, we can see that the knob that rotates the stage is connected to this little shaft here that spins. Let me see if we can't use that to our advantage. If I disconnect the O-ring that drives the stage, then twisting the rotation knob will only rotate the shaft and nothing else. If I then wrap some tiny metal wire around the shaft, then I can create a little wire reel. If I connect the other end to the mirror, then hopefully, when I spin the external knob, it will rotate the shaft, which will pull on the wire, and that will change the angle of the mirror. Moment of truth. Wow, I can't believe that actually worked. One thing I need to do now, though, is to lock down the stage and make sure it doesn't spin. Okay, perfect. Let's turn the microscope back on and see what this looks like. You can see that as we tilt the mirror, the brightness changes dramatically, especially at very steep angles. I set up the computer capture device and took a set of photos in order to measure this effect. It's clear that if we want to maximize the contrast, then we should obviously tilt the mirror as much as we can. However, there is an obvious problem. If we tilt the mirror too much, then only the samples in the very center of our image are going to have the mirror still underneath. The exact location of the sample on the grid will limit the maximum tilt of the mirror. That is an inevitable limitation of this type of STEM-in-SEM adapter. Okay, I think it's time to test a real sample, and I have just the thing. Gold nanoparticles. I showed how to make these in an earlier video. Let's see if we can put some gold nanoparticles on a TEM grid. I have here a FormVar-coated grid. The FormVar is an extremely thin plastic sheet that spans the holes in the grid. If you'd like to know how I made these, check out my last video. My goal is to create gold particles roughly 100 to 1000 nanometers in size, and deposit them on the formvar surface. I start by adding 10 microliters of a chloroauric acid solution on the surface of the grid. To that, I add 10 microliters of a sodium metabisulfite solution. This causes a chemical reaction where the gold comes out of solution and forms tiny spheres, or nanoparticles. Nanoparticles below 100 nanometers in size can generally remain suspended in solution, but the ones I'm making here are large enough that they should settle to the bottom. Alright, the reaction seems to be finished. Now I need to remove the remaining liquid. Let's see if I can wick up most of it with this Q-tip. And there we go. Awesome, that worked really well actually. Now I just need to leave the grid for a few more minutes to fully dry. Perfect. Let's transfer this to the sample holder and then put it in the SEM for testing. I don't know if it comes across on camera, but these grids are incredibly tiny. I'm doing my best not to mistreat these grids, but man, this is difficult. Come on, come on. There we go. Alright, that'll do. I reinstalled the shield and mounted the assembly back on the sample stage. Let's fire the SEM back up and see what this looks like. Okay, something is definitely wrong here. You can definitely see that we've created a whole bunch of nanoparticles, but check out this big one in the center. Do you see how it's very bright and looks three-dimensional? Yeah, that's not a transmission image. That is definitely a secondary electron image. The shield is supposed to completely block the secondary electron image, so clearly it's not working properly. Let's figure out why that is. So this is our current shield design. The idea is that any secondary electrons emitted from the surface of the grid will get blocked by the shield before making it into the detector. My original assumption was that the shield just needed to be placed in between the source of the secondary electrons and the detector in order to block them. However, what's probably happening is that the secondary electrons are being ejected in a way which allows them to bypass the shield and still make it to the detector. This could probably be mitigated if our shield were substantially taller. But how tall does it need to be exactly? Well, to determine that, I made this. It's a piece of aluminum with several holes of different depths. The expectation is that as the depth increases, fewer of the secondary electrons from the bottom surface will reach the detector, and the bottom surface will be darker in our image. This should give us useful data on how tall the shield needs to be. Here is the hole that's 1 millimeter deep. You can see that the average brightness is about the same inside the hole as it is at the top surface. This indicates that the hole is not deep enough to meaningfully block the secondary electrons. However, as we increase the depth to 2 millimeters, you can see that the surface at the bottom is noticeably darker, indicating that fewer of the secondary electrons are reaching the detector. As we increase the depth to 4 millimeters, you can see a noticeable improvement, which gets even stronger at 8 millimeters. And at 16 millimeters, the surface inside is basically pitch black, indicating that virtually zero electrons are reaching the detector. So this data tells us that our existing shield is definitely not tall enough. The problem is, our current design is already as tall as it can be without risking damage to the SEM. Are we doomed? Well, not quite. I took a look at our current sample holder and realized that we can probably make this shorter. The reclaimed height then can be used for a taller shield. I machined the sides off the bottom of the sample holder and then cut a matching slot into the base. And check it out. I managed to reduce the height by several millimeters at least. Now I can fit a much taller shield than before. And here is my new shield. It's much taller than before, and it has a smaller top hole. If you're wondering why I made it from brass, it's because I kept losing the tiny aluminum shields amongst the sea of other tiny metal objects in the shop. Brass is a lot more visible. Anyway, let's put this into the SEM and see if it works. Oh wow, that is a huge improvement. Take a look at the difference between the first and second shield. With the first shield, we very clearly saw the secondary electron image. With the new shield installed, the grid is basically black. This indicates that we have almost entirely eliminated the secondary electron signal that was plaguing us earlier. Now that we've done that, There's really only one more way to improve the image contrast further. We need to make the mirror even brighter. Fortunately, I know of an easy way to do this. The number of detectable electrons emitted from a surface greatly depends on atomic number. Aluminum is only atomic number 12, but gold is atomic number 79. If we were to coat the aluminum mirror in gold, then that would increase its brightness, which would therefore increase the contrast in our image. Ideally, I'd use a vacuum deposition machine to coat the aluminum piece in gold, but unfortunately, my vacuum deposition machine is in the shop right now. I think I have a reasonable alternative. This is the lid to the integrated circuit I showed in the first SEM video. It's a little awkward, but I can attach it to the mirror with some conductive tape. Perfect. Let's reinstall it in the SEM and see if that had an effect. It might be better. I think we've reached good enough territory. Alright, I think I'm satisfied enough with this apparatus. Let's check on those nanoparticles again. Okay, this looks promising. Alright, that actually looks pretty good. The nanoparticles appear dark and two-dimensional, which means that this is definitely a transmission image and not a secondary electron image. The new shield is a very clear improvement when it comes to blocking unwanted secondary electrons. But wait, I hear you say. The secondary electron images look way better than the transmission images. Why did we go to all of this trouble just to produce something that looks worse? Well, the answer to that is simple. It's because we're looking at gold nanoparticles. I chose gold nanoparticles as our test subject because they're suitably small and because I had them on hand. However, if you remember, dense metallic objects like gold are actually the best possible subjects for secondary electron imaging. If we want to show off the true capabilities of the STEM adapter, then we need subjects that produce poor secondary electron images. If you remember from earlier in the video, transmission electron imaging really shines when we use it to image organic materials, especially cells. So let's image a cell then. Well, not just yet. Cells actually require extensive preparation before they can be imaged in an electron microscope. For starters, cells are full of water, and if you put it into the vacuum of the SEM chamber, they will violently explode as the water in the cells suddenly boils. They also need to be properly preserved, then cut into incredibly thin sections and stained with exotic heavy metal salts like lead citrate and uranyl acetate. So cells will have to wait for a future video. However, I think I can find something organic and thin enough to produce a usable transmission image as a demonstration. I scavenged around the house and found this dead mosquito. I suspect that the wings might just be thin enough that they'll allow some of the electrons to pass through and create a usable transmission image. But first, let's take a look at it as a secondary electron image. This is the mosquito wing as it appears in an ordinary SEM. When we zoom in, we can make out a bunch of little hair-like structures all over the wing, as well as some other mystery objects scattered around. What's noticeable here is the general lack of detail. Organic material is mostly carbon, oxygen, and hydrogen, and these low-density atoms just don't emit that many secondary electrons, which makes our image pretty poor. Now let's try looking at the wing as a transmission electron image. I carefully placed the wing on the TEM grid. Let's see what this looks like in the microscope. Okay, so this is interesting. A few things are noticeable right away. First, the transmission image appears to have a lot more contrast than the SEM image. We can clearly see that the bottom half of the wing is thicker than the top half, which is nearly transparent to the electron beam. And when we zoom in, we can make out a lot more details in the small structures of the wing. And those random objects scattered around the surface, those are more detailed too, though I still have no idea what they might be. So I think that this at least proves that our STEM adapter is working properly. We've succeeded in adding transmission imaging capabilities to the Scanning Electron Microscope. So where do we go from here? Well, in order to achieve my goal of imaging cells, I need to acquire the ability to do the extensive sample preparation that cellular TEM images require. This process involves removing all the water in the cells and replacing it with solid resin, slicing the cells into 100 nanometer thick layers, and staining them with toxic heavy metal salts. However, all that is going to have to be part of a future video. If you happen to work in a lab that has access to an ultramicrotome or other TEM sample prep supplies and are interested in assisting me with this, feel free to leave a comment. Until then, I want to extend my thanks to my supporters on YouTube and Patreon. You guys are really fantastic, and I appreciate all the help you provided that makes these crazy projects like this possible. Thanks to your support, I've managed to acquire a cool new piece of lab equipment that I am super excited to share with you all in my next video. Make sure you're subscribed and ring the bell so you don't miss it. See you later.